So today we're going to look at graphing inequalities in two variables. And we're going to start with a real world problem where you would use this. So Hannah has a budget of $35. She's budgeted $35 every 3 months for car maintenance. From this, she must buy oil costing $3 and filters that cost $7 each. How much oil and how many filters can Hannah buy and stay within her budget? Here are some questions to think about. Please pause the video and think about these questions. So how many variables do you need if you want to write an inequality for Hannah's budget? Well, you need two of them. One variable has to represent the units of oil that she uses, and one represents the number of filters. Which inequality symbol would you would you use to write the inequality? Well, the symbol for less than or equal to, which is given, that's the one that you have to use because Hannah can only spend up to $35, and up to is a ceiling. A ceiling would be less than or equal to. The last question you thought about was, what inequality can you write to represent the situation? Well, it's $3 for the per unit of oil and $7 for the number of filters, and that amount has to be less than or equal to 35. This is where we would use a two-variable inequality to kind of get an idea, not only to get an idea, but to actually solve a real-world problem. So the first thing we want to look at is really, how do we get to this two-variable inequality? First, we started with a one-variable inequality. And this one right here in front of us says x is less than 3. Well, if we graph x is less than 3, since the variable is already by itself, we get this. Okay? Less than numbers go to the left. This is an open circle. Now, this open circle represents that electric fence that we talked about, but it also represents just that you can get as close as you can to 3, but you can't actually get to 3. Otherwise saying 3 is not a solution of what you're looking at. And how we want to look at this is if we're kind of looking down the hole of a pipe. What do I mean by a pipe? Well, if we look at a fence, if you look at a fence long ways, you see it looks kind of like a line. But if you look down into the circle of the fence, you can see that it goes, and it looks like a circle, kind of like the circle that we see here. Well, that's only one variable. So if we take a number line going this way, which is the one we used for x just now, and then we put another number line on it that doesn't interact with it in the same way. If I had a number line for y that was slanted, some of it would be in the x direction. So I don't want a number line that goes directly slanted with the x. I actually need a number line that's perpendicular. And so this other number line for y allows me to use two variables to describe something. Well, we already know what it looks like to have an inequality with one variable graph, but now we have to look at what it looks like with two variables. So if I take this fence and kind of turn it on its side, I basically have this. I take that circular hole for the pipe, which used to be over here, and now I turn it on its side. And if we really think about this, what are we saying? Well, x is less than 3. Well, every time we do these, we have to have a boundary number. Our boundary number for this was 3. Well, x is 3 over here, and x is 3 over here, and x is 3 over here, and down here, and over here. And really, all along this line, x is equal to 3. But it doesn't tell us anything about y, so we don't really care about y. We're not really looking to see what y is doing. We know that for all of the y's that we talk about, x is still 3. But that's our boundary, and remember there's no or equal to. So instead of having a bunch of open circles on a graph, we use a dotted line. And it's just like having an open circle here. If I turned it on its side, I would really want to see what that looked like. And that would look like a dotted line. Again, as you can see if you look down the picture on the left. So if we kind of just turn this way, we can see that we get a dotted line from these open circles. Well, we can't forget the arrow because both parts of this give us an answer. So if I take these arrows and I start to put them this way, notice what happens. These arrows don't actually change where they're going. They're still going to x's that are less than 3. And they're happening for all of the y values, because we don't have a y in this equation. We only have an x, in this inequality. We only have an x in this inequality. And so what we're really looking at is all those arrows pointing to the left. And so we no longer just have a line, we have what's called a plane. Okay? Basically like a piece of paper, like a sheet. As if you rolled out a piece of toilet paper, it goes off the roll, which would be the line, and just covers everything. Okay? And what we call that is a half plane. Why a half plane? Well, you could probably figure that out. Half of this graph, because remember this line goes in up and down and all in forever and ever. Half of this graph, all of the stuff on the left, is this half plane, and the other side would be the other half of the graph. That's why they call it a half plane. So now what we want to do is we're going to use this knowledge to our advantage. We want to use this knowledge. We want to put down our boundary line, which we definitely had before. We used to have a boundary point or circle, but now we have a boundary line. And then we want to decide which side of this makes the inequality true. We started with a simple one where we only had one variable that was changing, even though we put it on a 2-variable coordinate plane. Now we're going to look at some of them where the lines aren't just straight up and down or right and left, but slanted. So we have to talk about both x and y. So in order to do this, we need some steps. So the first thing we want to do for all of these is we want to solve for y in terms of x. Basically, we want to end up with our trusty, handy-dandy y equals mx plus b. We want to get y by itself. Step 2, we want to graph the boundary line with either a solid or a dashed line. Now, open circles went with a dashed line, so the closed circles that we talked about before would go with a solid line. The last part we have to shade, just like before we had to draw an arrow in the direction of the things we were talking about. This time we have to shade in the whole half plane in the direction that we're talking about. Okay? And the way that we're going to do that is we're going to use a test point. The test point basically tells us an x and a y value, because it's a point. And we test that point somewhere along the graph. The very important part about the test point that you do not want to pick it. It cannot be on the boundary line. Boundary with a D. Okay? Cannot be. And that's just to allow us to remember that when we're really looking at a boundary line, that's where the dot is, or the line now that we're using 2 variables. We're on a coordinate plane with 2 number lines attached. And so we don't want to pick the boundary as what we're talking about. We want to look for the half plane so we know where to shade. So let's actually do this. So first we recognize that it says graph. It says minus x plus y is less than negative 4. Well, if I want to do this, I have to first rearrange it so that we solve for y. So first solve for y in terms of x. So you take your original inequality. You're going to do the inverse operation to the x to move it to the other side so you can get y by itself. The y is already positive, so we're in good hands. And we get y is less than x minus 4. And so what I'm going to do is use that to my advantage. Now I have it in the form that I want. And the next thing I'm going to do is I'm just going to graph the boundary line. Remember, the boundary line is basically as if it was an equal sign. So that boundary is what we're going to look at. And then we're going to use the fact that it says less than to remember that that's a dashed line, not a solid line, because there's no equal or equal to here. So what we're going to do, this is my y-intercept. That's 0, negative 4. My slope is 1 over 1. So I have 1, 2, 3, 4, minus 4, and I go up 1 over 1, up 1 over 1, up 1 over 1, just what we do with any other line. I made a number of points so that I'd have probably a more accurate line. But now I have to remember, because this is not an or equal to, it's just a less than symbol, this is a dashed line. Remember, these lines go on and on forever in both directions. So I have to make sure that I put arrows on the end of my line. So it crosses at -4. Now I have to figure out, how am I going to shade this thing? And the beauty of this is we have to remember that we don't pick a point on the boundary line. We need to pick a point somewhere in the other half plane. So the point I decided to pick, and it doesn't matter, is +4, -1. Just to make sure, +4, -1 is not on my, oops, apologize. +4, -1, 1, 2, 3, 4, down 1, thank you. Okay, it's not on the line that I've graphed. It's not on this line at all. Okay, so now when I plug this in to my original inequality, I end up with a true statement. That true statement says that -1 is less than 0. -1 is always less than 0. So that tells me that all those arrows I used to use before to point me in the right direction, I'm just going to shade in this whole half plane. That's the half plane I shade in. Just to prove to you that it doesn't matter what side I choose, I still can figure out the right answer, I'm going to choose 0, 0. Okay? Why? Because that's an easy point to pick, and I can figure that one out also. Well, 0, 0 is here. I plug 0 in for x and 0 in for y, and what I find is this statement. That this statement is false. 0 is not less than -4. Well, I want to shade on the true side. I want to have a representation of what actually makes sense with my original inequality in two variables. So since 0, 0 is a point that doesn't make sense, the entire half plane that's not on the boundary line doesn't make sense. And the entire half plane on the other side definitely makes sense. So either way, if I find true on the side, I shade on that side. If I find false on the side, I shade on the opposite side. Always on the other half plane. Okay, always on the half plane that we're using. So we're going to do the same thing again. Just some more practice. So I'm going to isolate y. Okay, do the additive inverse to both sides. I get 3y minus 4 is less than or equal to -4x plus 6. I'm going to divide by 3, and notice I'm dividing each part, everything on both sides by 3. I'm dividing by a positive, so my inequality sign does not flip. And I get -4/3 x plus 2. My y-intercept is +2. My slope rhymes with m. My slope is -4 over +3. So again, I go up to 2 from my origin. Remember, this is the x-axis, this is the y-axis. And now I have +2 for my y-intercept. I'm going to go down 4, 1, 2, 3, 4. And 3 to the right, because it's down is my rise or my drop. And my run is going to be 3 to the right because it's positive. I'm going to do it again. Just so I get a little bit more of an accurate line. Okay? Now, I drew a solid line this time, just like I would have drawn a circle, a closed-in circle, or a solid dot. Because I have this or equal to. And the or equal to means that my boundary is included in my answer. That's my or equal to. So you guys would use a straight edge. When you do this, this is what you end up with for your boundary. Now I need a test point. So for me, since I like to make my life a little bit easier, I'm going to pick 0, 0. Because it's not on my boundary line, and that's very important. I don't want to pick a number on my boundary line. I want to pick it in one of the half planes. Okay? So I'm picking 0, 0. So when I plug that into the original, I get 4 times 0 plus 3 times 0 is less than or equal to 6. 0 plus 0 is 0, less than or equal to 6. That's a true statement. It's always a true statement. That means I shade on the side that's true. So since my 0, 0 is on that side, I'm shading on this half plane. I shade that half plane. And even though my lines don't go all the way, that whole half plane, because the line goes forever and ever in both directions, that whole half plane all the way down, out of the paper, out of the page, must be shaded. Okay? Even if I can't see it, it's shaded over there. I've completed the graph. The next thing I'm going to do is go way back to the original problem that we did all the way in the beginning when we talked about Hannah. So if I wanted to figure out where Hannah falls, how much can she spend, what can she do, what combinations of oil and filters she can use, I'm going to do exactly what I did before. So additive inverse again. Divide by 7 to get the y by itself. Make sure the y is positive. I'm dividing by a positive, so it doesn't matter. I'm going to divide both sides by 7 and everything on both sides to make sure I did this correctly. So I get minus 3/7 x plus 5. This is my boundary equation because I'm going to draft the regular line. I'm going to start with my y-intercept, which is 0, 5. Then I have my slope, which rhymes with m, minus 3/7. So 1, 2, 3, 4, 5. Then I'm going to go down 3, 1, 2, 3. And then 7 to the right because it's positive. Okay. I could try to go down 3 and 7 to the right again, but then I'd be off my graph. So I'm actually going to try to do the reverse of this and then put positive on the top and negative on the bottom, just to remind myself that I can go the other way. So if I go up 3, 1, 2, 3, and then I would have to go 7 to the left. And I still end up with a straight line. Okay, solid line again because it's or equal to. Now, I'm going to pick 0, 0 to see if this makes sense, because that's an easy one. Again, I can pick anything that's not on my boundary line. So when I do that, I get 3. So I'm picking this point to test. That's my test point. 3 times 0 plus 7 times 0 is less than 35. 0 is less than 35. That is true. So I shade on the true side. Last one, we're going to look at another type of real-world problem, but we're going to take this one all the way through. So Cami earns extra money by making and selling jewelry. She earns $2 for every necklace that she sells and $1 for every pair of earrings that she sells. If she wants to earn more than $20 per day, how many necklaces and pairs of earrings should she sell? So, as always, we read the directions first. It says, define variable, write an inequality, and graph the inequality to find the solution. So I first must define my variables. And so I noticed, just like in the first problem, I'm talking about two really separate things. So I'm going to end up with two variables. The x, so let statements, two let statements. The x is the number of necklaces she should sell, and the y is the number of earnings she should sell. Write an inequality. So that's what the next step. So I have to basically start with the words, and we've been doing this for a little bit. We're going to start with the words and then go to the inequality that goes with the words. Remembering now I have two variables as opposed to one. So 2 times the number of necklaces, since I've already written it down, helps me, is x plus, that's a plus sign, 1 times the number of earrings, 1 times y, is more than. Is more than means that I have to be more than whatever the next thing I'm talking about. Well, that's going to mean I have to be greater than. And is more than is telling us this. 2 times x plus 1 times y is greater than 20. This is my inequality. So I've defined my variable. I've written my inequality. Now I'm going to solve. Okay. I solve it this way, simplify it so that it looks like the y equals mx plus b form, even though this is an inequality. Then I have to really understand the problem. I have to understand what I'm going to do. So first, she can't sell a negative number of earrings or necklaces. So that doesn't even make sense to have a graph that has negative numbers for the domain, being your x's, or the range, that being your y's. So it doesn't make sense to have a negative part of the graph for the x and the negative part of the graph for the y. So we're going to end up in the first quadrant. Positive y's, positive x's. We also need to pay attention to some of the following things. This plus 20 means that that's the amount of money that's the amount of money we're looking at, okay? And then you're decreasing from there. So you're starting at the y-intercept, and then we're decreasing, all right? So the y-intercept is 20. Notice it goes all the way up there. I have to draw my graph. And so I've used this graph that was there before. You can start up at 20. You could also choose to do this a different way. Notice the slope is still minus 2. You go down 4 and 2 to the right. That's a negative 2 slope. And I need a test point. So I'm going to pick a test point of 8, 10. Okay? I could also pick a test point of 0, 0. Doesn't matter. So when I pick 8, 10, 10 is the y value, is greater than negative 2 times 8 plus 20. I end up with 10 is greater than 4, because negative 2 times 8 is negative 16. And so that's a true statement. It's always true, therefore I shade on that side. That's where this came from. Okay? In terms of understanding the problem, 8, 10 has an actual meaning. Okay? Since we defined our variables way back in the beginning, x is the number of necklaces. So that means that I can have 8 necklaces and I can get 10 earrings and still fall within my constraints, still fall within the things that tell me what I can't and cannot do. Okay? And that's what we're looking at. And so that's why this half plane is filled above this line to let you know that all of the things we're talking about needs to be greater than this. Thank you guys, and I'll see you guys tomorrow.